All right, go ahead and grab your notes if they're not already out. We need to finish up section 1.3, and then we're going to get into 1.4 today as well. A couple special limits. Notice on both of these, if you plug in 0 for x, which is the first thing you should always do, you do get 0 over 0. So sine of 0 is 0 divided by 0. The problem is on both of these, they're not easy to simplify any other way. So it's really just a theorem. The two things that you should know. We use the top one a lot more than we use the bottom one, but just in case the bottom one does pop up on a test, you know that as well. So the limit as x approaches 0 of sine x over x is 1, and the limit as x approaches 0 of 1 minus cosine x over x is 0. All right, those are two special limits that you should memorize for the chapter 1 test. So we'll take a look at a couple examples that deal with those two things. Example 1 asks us to evaluate the limit as x approaches 0 of tangent x over x. Tangent x over x. We want to rewrite that so that part of it looks like one of these two special limits. So in this case, tangent we know is sine over cosine. So I can rewrite it so that I have the limit as x approaches 0 of sine x over x cosine x. Notice part of that is one of our special limits, sine x over x, and I still have cosine x on the bottom. So based on the special limit over here, this is right here, number 1, the limit as x approaches 0 of sine x over x, this part's all going to go to 1. And make sure you plug in 0 into the rest of it. The limit as x approaches 0 of 1 over cosine x. Cosine of 1 is also 1. 1 times 1 is 1. So the limit as x approaches 0 of tangent x over x is 1. Example 2, a couple more of these. The limit as x approaches 0 of sine 3x over x. So it looks pretty similar to that first special limit, but instead of sine x over x, we have sine of 3x over x. One thing you cannot do is you cannot take the 3 and multiply it out front. Sine of 3x is not the same thing as 3 times sine x. To use the special limit, we want this and this to be the same thing. Well, I'm allowed to multiply the bottom by any number. So in this case, I want to multiply the bottom by 3, as long as I multiply the top by exactly the same thing. So multiply the top and the bottom by 3. So that's going to give me the limit as x approaches 0 of 3 times sine of 3x over 3x. The limit as x approaches 0 of sine 3x over 3x, that's our special limit. So this part's 1, 3 times 1 gives me 3. Take a look at one more of these special limit problems. I've seen one similar to this pop up on Sister Monica's test from time to time, so I want to make sure we take a look at it. The limit as x approaches 0 of sine to the 5th x over x to the 4th. Sine to the 5th x over x to the 4th. What you want to do on one of these, you still have the limit as x approaches 0. I want sine x over x. Well, I have 4 sine x's over x. That'd be sine to the 4th x over x to the 4th. Notice I have one more sine x on there. In order to get sine to the 5th x, I need to multiply it by sine x. So now I have 4 sine x's inside the parentheses, 1 on the outside gives me 5 times x's. And I've got x to the 4th on the bottom there, so I haven't changed my problem at all. The limit as x approaches 0 of sine x over x is 1. 1 to the 4th, it's still 1. Don't forget to plug in 0 into the rest of it. Sine of 0 is 0. So this one should be 0. That's the rest of section 1.3. Just a couple special limits. I think there is a homework problem that deals with the second special limit, the 1 minus cosine x over x. I will spend most of the time today on section 1.4. 1.4 is titled continuity and one-sided limit. It says a function f of x is continuous at the point C if. A continuous function should go through the point. All right, so a continuous function would look like that at x equals c. We're not going to have a break. We would say if I have a break here, so if it jumps from there to up here, that's not a continuous function. It doesn't continue through the point x equals c. Same thing if I have a hole at x equals c. All right, so if I have a hole at x equals c, it's not a continuous function. It doesn't continue through the point x equals c. All right. So the 3 things that have to be satisfied in order to have a continuous function. First of all, f of c must be defined. Notice the graph I have over there right now, f of c is not defined. Also, if I have a vertical asymptote at x equals c, all right, f of c is not defined. So again, that would not be a continuous function. The second thing that happens, or needs to happen, is the limit as x approaches c of f of x must exist. So we looked at this example before here. F of x is defined. F of c is defined. I do have a y value at x equals c, but the limit does not exist, so that would not be a continuous function. So the point has to be defined, the limit has to exist, and those 2 things need to be equal to each other. F of c needs to be equal to the limit as x approaches c of f of x. If we look at this graph right here, f of c is defined. I do have a y value right there. The limit does exist. As I get close to x equals c, I do have a y value, so the limit exists. But those 2 things are not equal to each other, so I still do not have a continuous function. Basically, in order to have a continuous function, that y value needs to be equal to the limit, which is still in that hole, so that I do have a continuous function that passes through that point x equals c. So we have to have a defined point, the limit must exist, and those 2 things need to be equal to each other. We're going to be talking about one-sided limits in this section. The notation looks like this. The limit as x approaches c from the right of f of x, or the limit as x approaches c from the left of f of x. So the plus sign here tells us that we are approaching from the right. The minus sign then would obviously tell us that we are approaching from the left. So instead of looking for the limit as x approaches c of f of x, sometimes that may not exist, but then the one-sided limit might exist. We'll take a look at an example of that here. All right, so we have a graph here. Give me a second to make that graph. So go ahead, you can copy down that graph real quick. The important point are this undefined point here at -1, 5. The defined point is right here at -1, 2. And the other important point is actually right here at 2, -1. So just spend a minute or two sketching that graph. It doesn't need to be perfect, but those 3 points are the 3 important points that we're looking at. And we're going to evaluate several one-sided limits. So the first thing we want says the limit as x approaches -1 from the left. Again, the minus sign here means from the left of f of x. So I've got a graph of f of x there. The limit as x approaches -1, we've done before. We've said that at x equals -1, since they're not the same, since they're not coming into the same y value, we said the limit as x approaches -1 does not exist. Now, the one-sided limit, as we approach -1 from the left, so from the left here, the y value is approaching 5. So we don't care what's going on the right side of -1. On the left side of -1, the y value is approaching 5. For the second one down there, the limit as x approaches -1 from the right. So now I want to approach -1 from the right, and only the right. The y value approaches 2. Since those two things are not equal to each other, as I approach from the left and as I approach from the right, I get 2 different y values. We've done this before. The limit as x approaches -1 of f of x does not exist. The second column there, now I'm approaching x equals 2. So the limit as x approaches 2 from the right. So I'm coming in from the right, x equals 2. The y value is approaching -1. As I approach from the left side, the y value is approaching -1. And since they're coming into the same point, the limit as x approaches 2 of f of x is also -1. So one-sided limits graphically, just looking at the graph, just come in only from the left or only from the right. In order for the limit to exist, those two things need to be the same. Taking a look at example 4 there, example 4 asks us for the limit as x approaches 4 from the right of f of x given a piecewise function. F of x equals 3x minus 2 if x is less than or equal to 4. F of x is equal to x squared plus 1 if x is greater than 4. Again, f of x is defined as a piecewise function. 3x minus 2 for all x values less than or equal to 4. X squared plus 1 for the x values greater than 4. I need the limit as x approaches 4 from the right of that piecewise defined function. Since we're looking for from the right, the limit as we approach from the right, you need to think through, okay, do I need to be slightly less than x equals 4 or slightly more than x equals 4? If we're approaching 4 from the right, we would be a little bit more than x equals 4. So I'm using the second function there. All you need to do is plug in 4 to the x. the limit as x approaches 4 from the right of f of x would be 17. If it asks what is the limit as x approaches 4 from the left of f of x, you would plug 4 into the top equation. We're slightly less than 4 this time, so we can plug 4 into the top, which would give me 12 minus 2, which is 10. What about if it asks us what is the limit as x approaches 4 of f of x? Well, we know the limit as we approach from the right is 17, and as we approach from the left is 10. Since those two values are not equal to each other, the two pieces are not coming into the same y value, so this limit does not exist. Just like on the last example, when we look at the graph, the first one here, we got 5 when we approach from the left, and 2 as we approach from the right, so the limit did not exist. If those two values are the same, if you get 17, 17, then the limit is at the surface 4 of f of x would also be 17. Couple more problems here. This one asks us to find the value of k that gives us a continuous function. So they set up a piecewise function for us again. F of x equals 3 plus x for the x value is less than or equal to 2. And f of x equals x squared plus kx plus 1 for the x value is greater than 2. We need to solve for the k value that makes the function continuous. One of the things that had to occur in order for us to have a continuous function was that the limit had to exist. So let's take a look at the one-sided limits here. Just like on the last problem, we can find the limit as x approaches 2 from the left of f of x. So if I'm approaching 2 from the left, that would be the top piece. So plug in 2 for x gets me 5. The limit as x approaches 2 from the right of f of x, we would plug in 2 into the bottom equation. So that would give me 2 squared is 4 plus 2 times k. I don't know what k is, so just leave it as k, plus 1. So we plugged in 2 into the top equation to get the left limit, 2 into the bottom equation to get the right limit. And then if the limit exists, we said those two values need to be the same thing. So we can set them equal to each other. 5 equals 2k plus 5. And then we should be able to solve for k. Subtract 5 from both sides. We get 8. So the limit must exist, so we can find the left limit and the right limit. Set those two things equal to each other, and you should be able to solve for the variance. The intermediate value theorem. The intermediate value theorem says that f of x is continuous on the interval from a to b, and k is any number between f of a and f of b, then there is at least one number c on the interval from a to b such that f of c equals k. Which probably means absolutely nothing to you right now. Go ahead, write it down here real quick. We'll talk about exactly what that means. We have a continuous function on the interval from a to b. It says k is any number between f of a and f of b there has to be at least one number in between A and B such that f of c equals k. Again, this is called the intermediate value. So let's take a look at what this is talking about. First of all, we have a function on the interval from A to B. So let's draw an interval A to B. It says k is any number between f of A and f of B. F of A and f of B are going to be the y values at x equals A and x equals B. So if I have a point right here, this point here would be f of A, and B is up here. We've got f of B. It says if we have a continuous function, there has to be at least one y value such that f of c equals k. So k has to be in between a and b. K is any number between f of a and f of b. So k would be maybe right here. If I have a continuous function, so I start at a and I end at b, if there's a continuous function, it doesn't matter what it does. This theorem saying that the x value k has to have, or I'm sorry, the y value k has to have an x value somewhere in between a and b. All right. This only works for a continuous function. If f of x is not continuous, so f of b was up here, this wouldn't necessarily have to be true. I have a function here that's not continuous, and there's no x value in between a and b for the y value of k. But if we do have a continuous function, no matter what it does in between a and b, at some point it has to cross through x equals k to get up to b. The problems that are on your test are similar to example 7. Example 7 asks us to use the intermediate value theorem to prove that the function f of x equals x cubed plus 2x minus 1 has at least one 0 on the interval from 0 to 1. So we're using the intermediate value theorem to show that there's a 0 on the interval from 0 to 1. In order to do this, first of all, there needs to be a continuous function. We have a cubic. Notice any x value would give me a y value. Any polynomial is continuous. Make sure you write down that f of x is continuous. I know for a fact that Sister Monica on the test will take off if you don't state that there is a continuous function. So f of x is continuous on our interval from 0 to 1. Since it's polynomial, it's continuous on the entire number line. So that's important. Make sure we find f of 0. So plug in 0 for x. 0 plus 0 minus 1 gives us negative 1. And we need f of 1. 1 plus 2. One plus 2 is 3, minus 1 gives us 2. So basically what we have here is we have points at 0, negative 1, and 1, 2, and we have a continuous function. Kind of makes sense that somewhere in between 0 and 1, we have to cross the x-axis. So in order to write your final statement, it should say something like, since f of 0 is less than 0 is less than f of 1, 0 is in between negative 1 and 2, and we have a continuous function, which we already stated, there must be a 0 on the interval from 0 to 1. basically, the value, the y value we're looking for, in this case 0, needs to be in between the two y values when you plug in the endpoints of the interval. Plug in 0, plug in 1. 0 is in between there. I have continuous function for the intermediate values there. So we have a 0 on it. All right. We're going to skip the last example here. We'll talk about removable discontinuities versus non-removable discontinuities next class. This is your homework assignment. It should be on your Chapter 1 schedule. Actually, don't even worry about what's written up there. Check your Chapter 1 schedule in order to get your homework